So this is Donna Nelson, Chemistry 3053, Organic Chemistry, and we're going to discuss Chapter 7. We're going to look at nucleophilic substitution and elimination reactions. We're going to use the group alkyl halides, that family of chemicals, as examples of these reactions. All these reactions you'll see will occur with many other families of compounds. So this is just the first of many, and you will see these reactions as we go along in the rest of this course. So today we're going to get down through reactions in biological systems. So we're going to look at the introduction and the nomenclature, SN2 reactions. We're going to look at nucleophilic strength and solvent effects in SN2 reactions in biological systems, and we're going to get down through section 7.5 today. So here we have alkyl halides, and you can see that the alkyl halides are carbons have a carbon atom bearing a halogen, and they will undergo substitution and elimination reactions. Of course, the X here is the halogen, chlorine, bromine, or iodine. The fluorocarbons are quite unreactive because the carbon-fluorine bond is just very strong. And so the vast majority of reactions you're going to see are going to involve chlorine, bromine, and iodine. You see here you have an sp3 hybridized carbon. Here is an alkyl halide with sp2, and here is another one with sp2 reactions, with an sp2 hybridization. And of course, you can also have alkyl halides with sp hybridization. But the important point is the substitution and elimination reactions you'll see mostly at sp3 hybridized carbons. There will be a few others, but the vast majority will occur at sp3 hybridized carbons. These others will react, but here they're not formally substitution and elimination reactions, and here they don't react quite so rapidly. It has to be set up in order to have this reaction occur. So the vast majority, what you will study, will be focusing on sp3 hybridized carbons. So this is the alkyl halide. This is actually a phenyl halide, and this is an alkenyl halide, or a haloalkene, a halobenzene. Now, so I hope that you have already read the first of the videos that I made using the document camera, because you will need to refer to that constantly throughout this chapter. And so you should have looked at it already so that you will sort of understand where we're going. If you haven't, you're not going to know the place of these reactions in the whole scheme of the chapter. This chapter is our largest chapter that we're going to be covering, and it also is one of the most difficult, if not the most difficult. And so you really need to look at that video, and you should refer to it constantly. Every time you have a new reaction type that is introduced, you need to go back and review and see the similarities and differences and how they all fit together. So here we're looking at just substitution and elimination, and we're going to continue looking at substitution, in particular the SN2, but right here we're going to be comparing substitution and elimination, just like you saw on, although not in so much detail, as I gave you in my video. So here you see that what is happening is you're getting a nucleophile substituted for the halogen here. And here you're getting loss of HX and a double bond is being formed. So this is the substitution, and here you're eliminating HX across the carbon-carbon bond, and you're having a double bond formed. So the reasons that they undergo the substitution is the halogen is electron withdrawing. That makes the carbon partially positive, and the halogen is bearing a partial negative. And so since this is partially positive, it makes it susceptible, and it actually makes it attract the negatively charged or the electron-rich nucleophile. And so here, this can easily depart with a pair of electrons, and the nucleophile can come in for backside attack. And so the carbon starts out bearing 4 bonds, and it winds up bearing 4 bonds. As the nucleophile comes in, the leaving group departs. So as the interatomic distance, the distance between the carbon and the nucleophile, as that decreases, the interatomic distance between C and X increases. So it's a smooth transition. As one comes in, the other one leaves. Okay? So it's simultaneously. It occurs simultaneously. So in many of these cases, in the vast majority of cases, you're going to see that you get multiple products. It's very rare to just get one product. There will be some cases, as in when you have a methyl halide, but in the vast majority of practical cases, you'll get multiple products. And so this becomes the goal, the realistic goals becomes just to predict the major product. You're almost always going to have minor products. And so, for example, here, when this reaction takes place, you're going to have this substitution reaction where hydroxide has substituted for chloride, and you're also going to have the elimination reaction where hydroxide has come in and plucked off the proton, and you're eliminating essentially hydrogen chloride across that carbon-carbon bond, creating a carbon-carbon pi bond. So this is a list of leaving groups, and you can look at the, this is in order of strongest acid to weakest acid, and you can see the pKa's. These are actually -11, -9, -7, -3. This table is in your book, and you can see up here that the strongest acid is also the best leaving group. This is the most stable, I- is the most stable base, and so I is a very stable anion. You'll have to think back on your REO, the factors that contribute to the stability of bases that we discussed in Chapter 3. Go back and review those, because you will need those during this chapter. Remember, as we were covering them, I said learn them now, because you're going to need them later on when we start discussing nucleophiles and electrophiles. And here it is. This is now. And so you're going to need them now. So you've got the best leaving group. These are good leaving groups. These are poor leaving groups because they are very unstable anions. Okay, and remember that as stability increases, reactivity decreases. And so here, this is the best leaving group because it comes off as a stable anion. Down here, this is going to be the worst leaving group because this is not a stable anion. This is very reactive itself. So, of course, it's not going to be a good leaving group because there's no driving force for it to depart. So, I've already discussed what alkyl halides are. As nomenclature, you're going to follow a lot of the same rules that you already learned. For alkanes, you identify and name the parent chain, identify the name of the substituents, assign a locant, the number, to each substituent, and you assemble the name alphabetically. The halide group is the key substituent. However, the halide group is just sort of lumped in with the alkyl groups. In other words, what you're going to see is that the halo substituent is treated like alkyl substituents in that it is a prefix. You're going to see later on, and it is alphabetized along with the alkyl groups. You're going to see later on that in the other families of compounds, as in alcohols and aldehydes, ketones, you're going to see that those functional groups are named as suffixes. So an alcohol is like butanol. The OL designates it's an alcohol, and the OL is a suffix. Here, the halide is a prefix. And so this family is a little bit unusual. It's a very common one. There are some others, but they're not so common as this family. And so you'll see this, mostly you'll be seeing that characteristic in alkyl halides, in that the halogen is named along with the alkyl groups as a prefix. So here you can see that this chloropropane, here the chlorine is in the 2 position, and you can see it is a prefix. So in the common name system, you might call it propyl chloride, but in the IUPAC system, chloro is a prefix. Here, see, bromo is a prefix, just like methyl, and they're alphabetized. So the halo substituents are treated just like alkyl substituents. So this is going to be very easy nomenclature for you to learn. You've essentially already had it. You can see here that this, here you count this one down, count down the longest chain, 1, 2, 3, 4, 5, 6, 7. So this is going to be a something, something, something heptane. Now you look at your groups. You have a methyl in the 2 position, a methyl in the 3 position, a methyl in the 5, a bromo in the 5 position. And so why do you not start numbering at this end? Because you have, going from left to right, you have a substituent at the 2 position. If you started numbering over here, your first substituent would be at the 3 position. And so you want to number it so that your first substituent has the lowest possible number. So this is going to be 2, 3, 3, trimethyl. And you want to put it in alphabetical order. So bromo, B, comes before M for methyl. So it is going to be 5-bromo, 2, 3, 3, trimethyl heptane. And when you prioritize the groups that are at position 5, it is bromo, and in this group is 2nd, and then the ethyl is 3rd, and so you're going in the clockwise direction, so it's R. And of course, notice that the CH bond is going back, away from you. Alkyl halide nomenclature. So I've said most of this already. Systematic name, halo, alkane, chloroethane. The common name is ethyl chloride. Dichloromethane, methylene chloride. Methylene chloride is a common name that is used very much in lab, and you do need to know the common names for these smaller compounds. You have come along at a time in history when we have not yet converted completely to the IUPAC names. And, you know, we may never convert completely to the IUPAC names. And even though when you submit a paper for publication, you would be required to rename Your compounds, if you use a common name, you would be required to rename them using the IUPAC nomenclature. It doesn't matter. The common names are used so much that you still need to know them. You still need to know them. Greek letters are often used to label the carbons of the alkyl groups attached to the halide. So the carbon directly attached to the halogen is the alpha carbon. This one more position away is beta. This is one more position away, beta, gamma, and as you go down the chain, alpha, beta, gamma, delta. The amount of branching at the alpha carbon affects the reaction mechanism you're going to see. So this is the carbon bearing the halogen. So here it is bearing one alkyl group. This is a primary carbon atom. This is a secondary carbon atom. It bears two alkyls. Here, this is bearing three alkyls. It's a tertiary carbon atom. And whether it's a primary carbon atom, and it's often abbreviated by 1 and the percentage, 1 and the degree sign, 2 degree, 3 degree, this is vastly going to impact its reactivity. A substitution reaction requires the loss of a leading group and a nucleophilic attack, of course. There are two possible mechanisms, as you saw in the video that I created for you. So one is a concerted mechanism where both the nucleophilic attack and the loss of the leading group occurs in the same step. As the nucleophile comes in, the X- departs. It will occur simultaneously. And so here you can see this is the product where the nucleophile has replaced X-. The other one, which you remember from the video, was where it happens stepwise. So the former one, the one you just saw, had one step in this SN2 reaction. One step, two molecules coming together in that one step. And so it is a second order reaction. That's what the 2 is for. It's a second order reaction. Now this, notice the title here is SN2. This is not an SN2 reaction, okay? But it's lumped in here with SN2 reactions because this is going to be contrasted against the SN2 reaction. So this is the stepwise mechanism. The stepwise mechanism is not an SN2 reaction. The stepwise mechanism is an SN1 reaction. You will recall that from the video that I created for you. And so the first step is loss of the leading group to form a carbocation, which is a high energy intermediate. If you remember the energy diagram, you have to go uphill to get to the high energy intermediate. That's the first step. And then you go over another energy barrier and back downhill to get to the products. You're going downhill overall, and that's what drives the reaction forward. So the first step is loss of a leading group. This is going to be the rate determining step because you are going from a neutral molecule to a charged molecule, and that is invariably uphill. So you're going uphill. This is going to be your rate determining step. Here you're going downhill energetically. This has an energy barrier, but it is not your rate determining step. This first one is your rate determining step, and you look and you see how many molecules are involved in the rate determining step, and it's 1. So this is an SN1 reaction, substitution, nucleophilic, first order. It's dependent on the concentration of that reactant. And so once you get to the carbocation, the nucleophile attacks the carbocation. They just collapse together, form a bond, and go downhill. So I hope that you see the energy difference, the difference in these pathways, and you just simply must know them. This is going to be so important to you throughout the rest of organic chemistry. You'll just have to know them as well as you know the alphabet. So this is, again, just drilling this in perhaps too much, concerted substitution. Notice how it's coming in from the back. It's coming in from the back. Remember, I have said repeatedly that the nucleophile has to occupy the antibonding orbital of the breaking bond. And the antibonding orbital is going to be on the side of carbon opposite to where the leaving group is. So the antibonding orbital is back here. The pair of electrons has to move in and start populating the antibonding orbital. And since it's an antibonding orbital, that's what causes this bond to break, because it's antibonding. And it starts, as soon as you start populating that, it weakens this bond. So, this happens in a concerted fashion. You already know substitution nucleophilic, second order. You should do the rest of this. How do you write the rate law? What is the rate law? The rate equals a rate constant times the concentration of the nucleophile times the concentration of your other reactant. So, the stereochemistry. So here you've got the thiolate. And so the thiolate is going to come in from backside attack. It misrepresents the reaction, putting it on this side. It is not on this side as it reacts. So this hydrosulfide is actually going to attack from the back side. The pair of electrons on sulfur is going to need to occupy or start populating the antibonding orbital back here. So just in your mind, envision this hydrosulfide coming in from the back side, not over here. And so when it starts populating the antibonding orbital, the carbon-bromine interatomic distance will start to depart, will start to increase. As the carbon-sulfur interatomic distance decreases, the carbon-bromine interatomic distance increases simultaneously. And so then you have the carbon-sulfur bond formed, and the carbon-bromine bond has broken. So the question there is, though, that how does the observed stereochemistry support the SN2 mechanism? In other words, how does it prove or support backside attack? Well, notice that you've had inversion of stereochemistry here at this carbon. This carbon started out S and it wound up R. Okay, so you've inverted the stereochemistry here. The same way that your umbrella might get inverted in the wind. Okay, so these three groups are just pushed to the other side of the carbon. They start out on that side of the carbon, they wind up on this side of the carbon. When that happens, the stereochemistry gets inverted. You might want to make a model to convince yourself of that, because you'll just have to know it. You will have to just understand it and feel it very, very well. So here, the electron density repels the electron, the nucleophile from the front side. So this is showing the antibonding orbital. So you've got the antibonding orbital over here. This is the empty antibonding orbital right back here. And you also have some on this side. But you're not going to have S minus. Let's go back and look at that. What you've got is an anion attacking that molecule. And so you know that bromine is electron rich. So S minus is not going to be attracted to bromide. It's not going to be attracted to the bromine in this molecule. What's happened is the bromine is high in electronegativity relative to carbon anyway, and it's pulled electron density off of carbon, and it's made the carbon poor in electron density. It's bearing a partial positive charge. And so S minus is going to be attracted to this side of the molecule. And as it moves in, it's going to occupy the pair of electrons on sulfur. One of the pairs of electrons on sulfur will start to occupy this anti-bonding orbital. And as that happens, this carbon-sulfur interatomic distance will decrease. And as that happens, the carbon-bromine interatomic distance will increase. Now, realistically, when these molecules are in the solvent, what will happen is you'll have this bromomethane, and you will have the hydrosulfide anion. And so you'll have this molecule, the hydrosulfide will come in and I mean, they may have many collisions before they actually react. They may bump together like this, and then it may come around and bump here, may bump here, and then bump there, and bump. And then when it finally comes around and bumps into the backside, that's what will create the reaction. If they don't bump together exactly the right way, you won't have a reaction. Or what could happen is the hydrosulfide could come in, and as it starts to come in, I'm going to change hands. So here you've got the bromomethane, and then when the hydrosulfide starts to come in, maybe it's coming in not quite at the right direction, but then it'll start to get attracted by the partial positive charge here. And so it will actually sort of change its direction. It can move, okay? It can rotate in space and then start coming in the right way. And calculations have been done that show that if you put the anion in and it's not quite aligned so that the reaction could occur, then it can happen, or it does happen, that it rotates some and gets in position and comes in and reacts. So that actually happens. Now, less sterically hindered electrophiles. Less sterically hindered electrophiles. Here are the electrophiles. These here, and we're talking about steric hindrance at the carbon bearing the leaving group. At the carbon bearing the leaving group. Carbon bearing the leaving group. Carbon bearing the leaving group. So here, this is a tertiary carbon bearing the leaving group. Secondary carbon bearing the leaving group. Primary and methyl. And since you have the nucleophile coming in from the backside attack, the groups that are here are going to create steric hindrance for the anion coming in. So it's very important what groups you have here as to how accessible the nucleophile is to that anti-bonding orbital. So here, if you have this, where you have three groups attached to that carbon, the nucleophile is not going to be able to get in there. The anti-bonding orbital is not going to be very accessible. Here it's going to be a little more accessible. Here it's going to be accessible easily, and here it's going to be very accessible. So this is the most reactive of the alkyl halides. So here are some relative rates. So you can see that as we go from methyl bromide to primary, secondary, tertiary alkyl bromides, and you increase the branching at that carbon bearing the leaving group, the relative rate decreases, and that's due to the steric hindrance. And furthermore, if you move away one carbon farther away, so over here we were talking about the alpha position, now we're talking about the beta position. If you increase the branching at the beta position, so here you have no methyls, a methyl, two methyls, and three methyls at that beta position, you can see the relative rate, once again, decreases as you increase the substitution. That's a steric effect. This is a steric effect, that's a steric effect. As you increase the branching, you increase the steric hindrance, and it makes it harder for the nucleophile to come in and do the backside attack, occupy the antibonding orbital. So, this is an energy diagram, which you've seen many times. The potential energy goes up, the reaction coordinate is going across. So here the reaction coordinate, it could be the interatomic distance of carbon-carbon, and it could be that interatomic distance is decreasing as we go from left to right. Or the reaction coordinate could be the carbon-bromine bond distance or interatomic distance. And it could be that that distance is increasing as we go from left to right. Okay, and it doesn't say which one it is, but usually it will be one or the other. Okay, there are other things you could use. You could use angles, you could use dihedral angles, but bond distances are the most common. And so here what we have is, as the reaction progresses, you go over the energy hill and then down to a lower energy product. And so you can see the energy of activation. This is an SN2 reaction. Okay, this is a kinetically controlled reaction because you're talking about energy of activation. You have a single step, one energy hill. That's going to be your rate determining transition state structure right here. This is your point of your transition state, and this is your transition state structure. Okay, it does not exist for a finite amount of time. This is the transition state structure. It is said that the reaction passes through the transition state structure. The transition state structure does not actually exist for any length of time. And so notice that you've got the carbon-carbon bond breaking simultaneously with the carbon-bromine bond, carbon-carbon bond forming simultaneously with the carbon-bromine bond breaking. And so you've got a partial negative over here. You've gone from negative to partial negative because this bond is starting to form. Now you've gone from neutral bromine to a partial negative on bromine because the bromine is departing and becoming bromide. This is an SN2 reaction. So now let's look at these. So here we have we're going to compare the potential energy diagrams of SN2 reactions where you have an increasing amount of steric hindrance at the carbon atom bearing the leaving group. Carbon bearing the leaving group. Carbon bearing the leaving group. Here you have no methyls, one methyl, two methyls, and when you have a third methyl, the reaction doesn't occur. And so here you can see that here is a typical SN2 reaction, potential energy curve, and you can see here's your energy of activation. And as you increase the substitution, the energy of activation goes up. As you increase the substitution, the energy of activation increases similarly. Okay, that's because the nucleophile coming in from the backside attack has to overcome the steric hindrance that is created by the methyls. And so you can see that by the larger, the higher energy hills, the greater energy barriers. The nucleophilicity, if you have a strong nucleophile, the reaction will occur much faster than if you have a weak nucleophile. Of course, in some cases, if the nucleophile is too weak, the reaction just doesn't occur. But you need generally, you need a strong nucleophile for an SN2 reaction. So here you can see this is a strong nucleophile. It comes in, occupies the antibonding orbital, the iodide departs. The rate of this reaction is fast, especially compared to this. Here you have water coming in and doing a backside attack. And this is a very slow reaction. You'll notice that you're going here from an anion. You start out with an anion, you wind up with an anion in the product. Here you start out with two neutral molecules, you wind up with a cation in the product and an anion in the product. So indeed, this is going to be a slow reaction. And this is true generally. If you have a charged nucleophile, it will react faster than a neutral nucleophile. This is where you need, remember that the less stable the anion is, the more reactive it is. So hydroxide is less stable than water, and so hydroxide is going to be more reactive than water. Go back and review your reactivities of REO. Remember, REO describes anion stabilities for the purposes of equilibria, for the purposes of the stabilities of acids and bases. But nevertheless, you will be able to use that information here because it will form part of the rules for reactivities of nucleophiles. The factors that contribute to the strength of a nucleophile. This is one example. If you have a neutral molecule, it's going to be a weaker nucleophile. And then you have all of the REO factors that you need to review, and then you're going to have steric hindrance, which is more significant than the REO factors, and then you're going to have polarizability, which is more significant than the REO factors also, but you'll need to know all of those. And you do remember what REO stands for: atom, resonance, induction, and orbital. The orbital was controlling the electrons. So you'll need to go back and review that. And this section 7 doesn't really describe much. It doesn't tell you to go back and review REO. It talks a little bit about polarizability, maybe one sentence. Talks a little bit about steric impact, but we've already reviewed that. We've reviewed the sterics. Now we've reviewed charged versus uncharged nucleophiles. And so we're going to look at polarizability in a few minutes. And so it's not occurring in any one place in your chapter, but I'm giving it to you now in just these last few sentences in this presentation. That will probably be the only place that you're going to get it all summarized nicely in one place. So now, common nucleophiles, these are commonly used nucleophiles in substitution reactions. So here, weak nucleophiles are going to be less reactive because they're uncharged. Okay, they're neutral. A neutral molecule is generally less reactive. These are stronger because these are charged. So there's your two categories. This demonstrates again what you just saw a few minutes ago. And what you're going to see is these form some groups. You can see here's hydroxide, alkoxide. This is thiohydrate, and this is thiolate. And here are your halides. So you're going to see that your hydrosulfide and your thiolate, remember, sulfur is in the same family as oxygen, but one below in the periodic table. And so the sulfur is going to be more polarizable than the oxygen. Okay, and so even though the oxygen may have a higher electronegativity and it may be more reactive in some ways, here, as a nucleophile, these are going to be more reactive because of their polarizability. So these two are more reactive than those. The sulfur anions are more reactive than the oxygen anions as nucleophiles. And similarly over here, iodide is more reactive than bromide or chloride because of its polarizability. Okay, so polarizability increases as you go down the periodic table. So you can remember that here in these families. Polarizable atoms are good nucleophiles, so that's going to be iodide and S-. Now, also, the solvent can affect nucleophilicity, and in some cases, reverse it. So, you're going to need a polar aprotic solvent for SN2 reactions. So, why is that? So, a polar aprotic solvent is one, remember, that has no hydrogens attached to highly electronegative atoms. So this is a protic solvent. Hydrogen attached to oxygen, hydrogen to oxygen, hydrogen to nitrogen, hydrogen to oxygen. Over here, you don't have any hydrogens attached to highly electronegative atoms. So what is going on there? What's going on here is that these can participate in hydrogen bonding. And if they participate in hydrogen bonding, they will stabilize the anionic species. So if you have hydrogen bonding in the presence of these anions, you're going to have the solvent molecules will just cover these anions, and the anions won't be able to attack because they won't be able to slough off the solvent molecules to move in and attack. And so you need solvents that will not strongly solvate those anions, and that will be these, the polar aprotic solvents. Moving to a polar aprotic solvent will increase the rate of an SN2 reaction because it makes the anions, the nucleophiles, more bare. And that is what you want if you are going to have a reactive nucleophile. And so here, you have no interaction with the nucleophile, no interaction. Okay, this is an aprotic solvent molecule, DMSO. And so if you have a protic solvent, you're going to have it's stabilizing the anion, and so you're going to have a much higher energy hill. If you have a polar aprotic solvent like this, the anion is not stabilized, so it starts out higher in energy, so the energy barrier is lower, okay? The energy of activation is lower if you start out with the anion not stabilized. Biological alkylation. So methyl iodide is the most common molecule that's used to methylate biological reactions, and I'm not talking about in the human body, I'm talking about in the lab. Methyl iodide is very commonly used, but it's because you can do an SN2 reaction, come in, iodide departs. This is similar to methyl iodide in that when the nucleophile or the biological molecule comes in, it can do a pair of electrons on one of the atoms in that biological molecule, can do an SN2 attack on methyl, and this molecule, it becomes the leaving group and it will depart. So these are called methylating reagents because your biological molecule will come in and do an SN2 attack on methyl, and you've got a good leaving group, and so it will simply depart. So those are the first 5 sections, and now we'll go on to the